Ladies and gentlemen, good afternoon. I am Tamires and I will present the paper Chuchi's Development of a Robot Head to Reproduce Face Emotions Using 3D Printing Technology. I apologize for my English. I will do my best to explain the content presented in the paper. This presentation is divided into these topics: the objectives and contribution of the robot head, the motivation to develop a low-cost robot head using 3D printing, the development step of the robot head. In these two topics, I will present some videos that show the results found in the simulation and the real experiment. Finally, conclusions and future works. Let's start with the objectives and contributions of our paper. The main objective of this presentation is to show how the Chuchi's robot head was developed. Its name was defined using its developers' name Tamires and Tanaka. Chuchi's is a robot head inspired by a human head, that is my head. Chuchi's is open source and the files are available on the GitHub. Also, it is low cost and developed with 3D printing. Chuchi's reproduces the 6 basic and universal emotions, known as happiness, fear, disgust, anger, surprise, and sadness. To explain the contributions of this work, it is important to present some robot head found in the other papers, with the same characteristics as Chuchi's. For example, mechatronic head was based on the FAPESP methodology. This methodology is briefly explained in this presentation. The face was developed using a CT scan, and EVA was designed with low cost, open source, and also using FAPESP. As a contribution, only Chuchi's has these characteristics, in addition to having 14 several modes, a quantity considered low compared to other robot heads. Now, let's talk about our motivation to develop a robot head. Because the Chuchi's has a behavior close to those of human beings, she helps to create empathy and improve human-robotic interaction. She can be a receptionist in the hotel, health area, and other applications with human interactions. Development steps. This figure shows the steps used to develop the robot head. The eye divided into 3D modeling of the human head, and construction and validation. The first step was to develop Chuchi's CAD 3D from a CT scan. The CT guaranteed the precise characteristics and dimensions of the skull and jaw of my head. Radiant and the Mesh Mixer were used to visualize and convert the XM into CAD 3D. It is important to point out that because the CT scan is a procedure done by a human being, the work was submitted and approved by the Ethics Committee of the Federal University of ABC. The next step was to develop the virtual Chuchi's in Autodesk Fusion 360. The CAD 3D was imported into Fusion and its entire movement system was developed in this step. Here we can see the box that hold a part of the electronic project. The several models, in blue, are used to move the eyes and other parts of the head. During the modeling step, the electronic project was defined because the size of the electronic components affect the size of the Chuchi's. This figure shows the components inside the base of the Chuchi's. In it, we have a Raspberry Pi responsible for control all the components of the robot head. A camera is used in the vision system. A microphone is part of the Chuchi's hearing system, and a speaker that emits the voice of the Chuchi's. The several models were used to the foreneck region, and this model for the other parts of the our robot head, to drive the 14 servo motors of the robot head. A PCA 9685 model was used to connect the servos at the Raspberry. For powering all components, an external power supply was used. Finally, two coolers were installed in the box to ensure ventilation at the base of the two chips. The virtual two chips was simulated in diffusion with an API in Python, which allowed it to validate the robot head's movements. Now, let's talk about emotion. Two cheese emotions were based on Paul Ekman FAPESP methodology. As FAPESP, its movement of the face is called an action unit. The combination of some AUs forms the 6 basic and universal emotions. To validate these emotions, a system was implemented, which will be explained in the following slides of this presentation. As the next step in developing two cheese, we have the real experiment. Churches was developed using 3D printing technology. The filament used was PLA. In this step, the assembly and implementation of the electronic project were carried out. This figure shows some of the dimensions of the robot head, as the distance between the skull and jaw, the height of the shoulder, and the size of the base of the two teeth. Its weight is approximately 5.5 kg. A Raspberry library was implemented to drive all 2T servo models and the real experiment. The 2T has 80 degrees of freedom distributed and the horizontal movement of the eyes, opening and the closing of the eyelids and jaw, vertical movement of the eyebrows, mouth and the neck with horizontal and rotational movements. Now, I'm going to present some videos showing the 2T's basic movements during the simulation and the real experiment. It is important to highlight that the movement orientation is related to the robot. First, this video shows the virtual and the real 2T's eye movements. The movement is performed to the left and the right. Now, the movement of eyebrows moves up and down. The head movements are left, right, up, down, and a small tilt to left, and the right. Finally, jaw movements, partial and completely open. Now, I'm going to explain about 2T's emotions. To analyze and validate the 6 basic and universal emotions of 2T's, a software was implemented using the OpenFace library. This software compares the action units in each emotion on my face to the virtual 2T's and the real 2T's. The emotion of happiness, for example, is represented by the AU6 which are those green dots on the figure. AU12 and axillary 25 are located in the mouth region. Now, I'm going to show a move that represents the emotion of happiness on the three faces. This graph was generated to understand and compare how we use of its emotion were identified on my face, virtual touches, and the real touches. It can be seen that the x-axis represents the AU and the y-axis the intensity of its AU. The black bar are my data, the white is related to the virtual touches, and the gray bar are data of the real touches. The graph showed that the AU6 was identified on my face and the real touches face. This result means that this AU relates to the eye region more visible on the face of the real touches. Also, please note that the AU12 and axillary 25 in the mouth region were located on the three faces. It means that the virtual and the real touches reproduce the facial expression of this region. The idea explained in the previous slide was applied to all other emotions of fear, disgust, anger, surprise, and sadness. Therefore, the results found in the simulation and the real experiment are presented in the next slide. Finally, conclusions and future works. After finishing the development of the touches, we found that the city allowed a greater realism in touches mechanical structure. Regarding emotions, the results showed that the virtual and the real touches were able to reproduce this emotion of happiness, fear, disgust, anger, surprise, and sadness. These are the 6 basic and universal emotions. However, the intensity of its AU in identifying the virtual and the real touches compared to my face was influenced by the lack of artificial skin, changed the position of some landmarks in those regions highlighted in the figure. The emotion of happiness showed more similarity in identifying the AU and real touches compared to my face. Anger showed more stability in the data of the three faces, as it is an emotion with the most identifying AU in faces with skin. The best results found in this work were related to surprise and sadness emotions, identified on my face, virtual touches, and the real touches. As future works, to improve the results, an artificial skin will be developed to help the touches in reproduction of emotions. Its vision, hearing, and the voice systems will be developed so that the robot head can communication during a human-robotics interaction. I would like to thank the Federal University of ABC, NTU, FAPESP, and CAPS for supporting the development of this work. These are the main references of this presentation. Thanks so much for everyone to attend my presentation. Please feel free to contact me by email if you have any questions.